Assalamu alaikum everyone. I'm waiting for some other students to join. Just give me a minute. By this time, hopefully they will join and we'll start our class. Okay, dear students, I would like to start the class right now. Let us share the screen. So you can see the screen, right? So today I'm going to discuss specimen paper 2 of 2016. So go through these questions. Question number 1. Elements and compounds which have small molecules usually exist as gases or liquids. Chlorine is a gas at room temperature, whereas bromine is a liquid under the same conditions. Explain these observations. So 2 points, 2 marks. Your chat option is open. So hopefully you will use it properly. Okay. So chlorine is a gas at room temperature, whereas bromine is a liquid under the same condition. You can answer me in the chat option. Can you hear me, dear students? Can you hear me? Okay, thank you. Uh, So you can answer me over there. Let's go for the next one. We will be I will answer all these questions after a while. So you try, and whenever you write your answer, I can check it on the chat group as well. The gases nitrogen and carbon monoxide are isoelectronic. Isoelectronic means they have same electronic configuration. That means they have same number of electrons. Uh, that is, they have the same number of electrons in their molecules. Nitrogen molecule will have 28 electrons. Carbon monoxide will also have 28 electrons. Suggest why nitrogen has a lower boiling point than carbon monoxide. So this is B. Yes, a part is correct for the first one. There are 2 marks for this question, so you have to give 2 points. Fewer electrons in chlorine than bromine. Yes, correct. Weaker van der Waals force of attraction in chlorine compared to bromine. Yeah. So there are 2 points. Absolutely right. B suggests why nitrogen has a lower boiling point than carbon monoxide. Why nitrogen has a lower boiling point than carbon monoxide? You have to answer this question. You can see carbon monoxide. In question C also they have given a dot close diagram for carbon monoxide. From this one you can easily understand that carbon monoxide is a polar molecule, right? Carbon monoxide is polar because the electronegativity of carbon and oxygen are different, whereas nitrogen molecule we have 2 nitrogen atoms and their electronegativity are same. So not the triple bond boiling point. Boiling point, we'll talk about the polarity. Carbon monoxide is a polar molecule, whereas nitrogen is a non-polar molecule. Nitrogen is a non-polar molecule. Triple bond is a fact over there. In carbon monoxide also we have a triple bond. You can see that triple bond is also present in carbon monoxide. Can you see? Tausif, can you see that there are triple bonds between between carbon and oxygen? See the dot close diagram given in question C. In nitrogen we have a triple bond. In carbon monoxide we have also a triple bond. So in terms of triple bond we cannot explain. In terms of polarity we have to explain. In nitrogen molecule we have only van der Waals force of attraction. We have only van der Waals force of attraction, whereas in carbon monoxide we have permanent dipole interaction. And you know that permanent dipole interaction is greater than van der Waals force of attraction, which is why a high energy will be needed to break down this bond, and hence the boiling point will be higher. Furthermore, when we break down the when we think about melting point or boiling point, we just overcome the intermolecular force of attraction. We don't break down the covalent bond. When molecules participate in reaction, at the time these bonds need to be broken. I mean, chemical bond needs to be broken only when chemical reaction takes place. But boiling point, boiling, melting, these are physical changes. State of physical change occurs here. So when you are boiling carbon monoxide or nitrogen, you are just overcoming the intermolecular force of attraction. So you need to see what sort of intermolecular force of attraction is present. Your concept should be 100% clear. What sort of intermolecular force is present in nitrogen and what sort of intermolecular force is present in carbon monoxide. In carbon monoxide we have permanent dipole interaction. On the other hand, in nitrogen we have only van der Waals force of attraction. And you know that there are 3 types of intermolecular force. One is hydrogen bonding, another is permanent dipole interaction, and third is van der Waals force of attraction. Hydrogen bonding is the strongest, then permanent dipole interaction. Sometimes we call it dipole interaction, and then the van der Waals force of attraction. In carbon monoxide we have permanent dipole interaction. So obviously this is stronger than van der Waals force of attraction in nitrogen. Hence the boiling point of carbon monoxide will be higher. Now come to question C. Look at this diagram, and on the structure draw a circle around a pair of electrons that is associated with each of the following. a coordinate bond, a covalent bond, a lone pair. Let us come to covalent bond. When electrons are equally shared between atoms, we call it covalent bond. When electrons are equally shared between two atoms, at the time this particular bond is known as a covalent bond. On the other hand, a coordinate bond is a special kind of covalent bond. It is a special kind of covalent bond, not a regular type of covalent bond. Special type of covalent bond where a particular atom provides both the electrons for sharing. A particular atom shares both the electron, whereas other electron doesn't provide any electron. Okay, so you can see in this structure, when you are showing dot and cross, this will be covalent bond. Dot and cross, that means one electron is coming from carbon, dot electron is coming from carbon, and cross electron is coming from oxygen. So this is a covalent bond, whereas both the electrons are cross in between carbon and oxygen atom. You can see there are two electrons, okay, there are two electrons which are shared between carbon and oxygen, but this is coming from oxygen only. This is not coming from carbon at all. So this is a coordinate bond, whereas in the side of carbon or in the side of oxygen, we have two electrons each, dot electrons, two dot electrons here or two cross electrons here. Both these electrons, these are lone pair. Okay, these are lone pair electrons. I can do one thing. I can go for a new share. You can see the drawing, right? Okay, no problem. Just a moment. I hope you can see it easily. Okay, here I have drawn the. You can see it. Now you can see it, right? Okay, look at this. I have shown these bonds. I have circled already. Look at these two electrons. These are one type of electrons which are only shared by oxygen, not by carbon. So these are coordinate bond. These electrons are lone pair. These are lone pair, and you see dot and cross. Both are this dot electron is shared by carbon and cross electron is shared by oxygen. That means this is a regular type of sharing. This is a special type of sharing, coordinate bond. Regular type of sharing, covalent bond. And the electrons which are not participating in bonding are known as lone pairs. So these two cross electrons or these two dot electrons are lone pairs of electrons. Okay, any problem? So let's go for the next one. Okay, let's go for the next question. Try this one. Hydrogen cyanide is a gas which is also isoelectronic with nitrogen and carbon monoxide. Each molecule contains a strong triple bond with the following bond energies. Look at the bond energies. In this case, we are thinking about breaking down the covalent bond. We are thinking about breaking down the covalent bond, okay? Because the bond energies are given. In this case, we are not considering the intermolecular force of attraction. Intermolecular force of attraction will be considered for covalent molecules when we think about their melting or boiling. Understood? When we think about their melting or boiling, at the time only we will be talking about their intermolecular force of attraction. Because when we melt or boil, we do not break down the covalent bond. But when we carry out the reaction, at the time we have to break down the covalent bond. Now you see that all these three compounds, hydrogen cyanide, C triple bond N in hydrogen cyanide, or nitrogen triple bond, or carbon oxygen triple bond. All these three bonds are all these three types of bonds are triple bonds, right? Although each compound contains the same number of electrons and a strong triple bond in its molecule, carbon monoxide and HCN are both very reactive, whereas nitrogen is not. So you need to explain a reason behind this. So what could be the reason? Already I explained earlier the effect of dipole moment. In nitrogen, it is a non-polar molecule, so there is no dipole at all. Nitrogen is very reactive. Nitrogen is unreactive, whereas carbon monoxide or HCN are very reactive. Carbon monoxide and cyanide, in both cases we have a dipole, but nitrogen does not have a dipole. This is the reason. Let's go for the next one then. HCN reacts with ethanol, CH3CHO. Give a displayed formula of the organic product formed. So take a piece of pen and take a piece of paper and pen where you can write this displayed formula. Draw this one, everyone. No strong dipoles. No, you cannot say strong dipoles. You have to say that it doesn't have dipole. Carbon monoxide and HCN has dipole, but nitrogen does not have any dipole, because both the atoms have the same electronegativity. How the dipole will form? There is no dipole. So if you use a strong dipole, this is not correct. Okay. So give the displayed formula of the organic product. See, ethanol. You know that carbonyl compounds undergo nucleophilic addition reaction. So with HCN, it will also undergo nucleophilic addition reaction, right? So what will be the displayed formula of the organic product? Hopefully you have completed by this time. So let's come to this one. A1 I have drawn here. Basically C double bond O was there, and H remains as it is. You can see it here. The CH3 remains as it is. CH remains as it is. C double bond O in this case, and C double bond O, there will be difference in electronegativity. So oxygen will be negative, and carbon center will be positive, where cyanide will attack. And it will form CCN, and then with the oxygen, hydrogen will come, and this is how we can get this compound. Now, what type of reaction is this? Nucleophilic addition, and I have also drawn the mechanism here for your better understanding, so you can see the mechanism. Look at this mechanism. CH3, CH, C double bond O. This is having partial positive charge. This is having partial negative charge, because oxygen is more electronegative. So electron density will be pulled by oxygen. Once electron density is pulled by oxygen, this carbon center will be positive. So cyanide will definitely attack here. When cyanide attacks, we get cyanide in this way, and oxygen center will have a full negative charge, because it will take 2 extra electron. Because of this one, it will have a negative charge. Now it can attack a hydrogen cyanide. So from hydrogen cyanide, there will be H plus and Cn minus. So H plus will be attached to oxygen, and hence we get OH. You can see cyanide remains as it is, hydrogen remains as it is, CH3 remains as it is. So this is the change. And when hydrogen ion is coming, hydrogen ion is being attached to oxygen. At the time, cyanide ion is formed. So cyanide is working as a catalyst. In the beginning, cyanide attacks the carbon center, and the reaction begins, and at the end we have seen that cyanide is coming out. So this is working as a catalyst. Cyanide is working as a catalyst here, and this is how we get this product. That means hydroxynitrile. This is hydroxynitrile. In the second carbon we have hydroxy group, so this is 2-hydroxypropanenitrile. This is 2-hydroxypropanenitrile. That is the name of the product. I hope it is clear. You please respond in the chat group. So if you have any question, I will explain it again. Or if you don't understand anything, you can tell me. Otherwise, respond me if you understood so that I can proceed to the next question. If you have any doubt in question number 1, you can tell me. I'm just making it a bit bigger so that you can see it properly. Thank you very much, Bushra, no doubt. Okay, so we can proceed to the next one. Thank you for your feedback. Thank you. So we will go to the next one. Let's see. Let's go for the next question. Question number 2. Look at this. The diagram below shows for a given temperature T, a Boltzmann distribution of the kinetic energy of the molecules of a mixture of two gases that will react together, such as nitrogen and hydrogen. The activation energy for the reaction EA is marked. Okay, so you see activation energy is marked. Let me tell you something about the graph. In the beginning, see the x-axis and y-axis. In x-axis we have shown energy, in y-axis we have shown the number of molecules. So what can you see from the graph? There will be a very less number of molecules having very less energy, and there will be very less number of molecules having very high energy. Majority of the molecules will have average energy. You can think about your class only. The students with very high marks and students with very low grades or low marks are very less. On the other hand, most of the students will have average marks, right? So molecular energy will be similar. Most of the molecules will have average energies. See, the peak of the number of molecules with respect to energy is found here. That means average number of molecules will have a mediocre energy level, right? And this is the activation energy. You know what activation energy is. This is the minimum energy to start a chemical reaction, right? Activation energy is the minimum energy to start a chemical reaction, or the molecules must have this energy in order to start a chemical reaction, right? Now let's see what they are asking. Okay, now you see, draw a new distribution curve, clearly labels T dot for the same mixture of gases at a higher temperature T dot. So you can draw this one on your paper right now. Draw this graph on your paper. I'm giving you 2 minutes. It won't take more than 2 minutes. The next one also, mark clearly as H the position of the activation energy of the reaction at the higher temperature T dot. And then explain the meaning of the term activation energy. Thank you, Safia. Your answer is correct. You can see I think you can see my drawing here. Can you see the drawing? Dear students, can you see the drawing? I hope you can see the drawing. You see the full lines and the dotted lines. The dotted line indicates the higher temperature, T dot. As per the question, I have drawn this one at higher temperature, T dot. You see the peak is shifted towards right side. The peak is shifted towards right side, and at higher temperature, the number of molecules having very low energy is less, and number of molecules having very high energy is still less, but it is higher than the number of molecules in low temperature. At low temperature, less number of molecules will have higher energy, and at high temperature, more molecules will have higher energy. Now EA, look at EA. EA remains same for higher temperature and lower temperature. we don't change activation energy. You can think about activation energy as the pass mark. Pass mark remains same. Pass mark remains same. When students study properly at the time, their capability increases and the average number of students passing that particular subject increases when they study properly. Okay, but the pass mark remains same. In this case also, when we apply higher temperature, at higher temperature, activation energy remains same, but the number of molecules having activation energy or more increases. You can see the area. Look at this activation energy EA. This is the full line. The solid line shows the graph at low temperature, the solid line, and the dashed line shows the graph at lower temperature. The dashed line shows the graph at lower temperature. Look at this. So think about the energy after this one. After this one, obviously more number of molecules will have higher energy, right? More number of molecules have achieved activation energy. That's why the rate of reaction will be faster. Rate of reaction will be faster. I hope I answered this question. Now let's go back to the question once again. Let's go back to this question. Explain the meaning of the term activation energy. Already you have explained. Come to this one. The reaction between nitrogen and hydrogen to produce ammonia in the Haber process is an example of a large scale gaseous reaction that is catalyzed. So what is the catalyst? You know, iron is the catalyst. What is the temperature? 450 degrees Celsius the temperature and 200 atmospheric pressure. So you know it, right? Okay. Next one. On the energy axis of the graph above, mark the position clearly level C of the activation energy of the reaction when a catalyst is used. You know how catalyst performs in the reaction. Catalyst lowers the activation energy. Catalyst lowers the activation energy, but it doesn't change the energy diagram of the molecule. What I mean is energy diagram of the molecule remains same. I will go back to the graph. You see the question once again. On the energy axis of the graph above, mark the position clearly level C of the activation energy of the reaction when a catalyst is used. Use your answer to explain how the use of a catalyst results in reactions occurring at faster rate. Okay, you have seen the question, right? So I can go back to the drawing so that you can understand what I want to explain. Okay, look at this one. In this graph, they asked us to level C here. Suppose we have given a random activation energy. It is not the peak. It is not the peak. Don't misunderstood. It will be obviously in the left side of the previous activation energy because activation energy increases. Look at this one. This is our activation energy for C. Activation energy catalyzed. This is activation energy uncatalyzed. The right side, there is a vertical line. You can see, right? The right side, the vertical line represents the activation energy without catalyst. And in the left side, the vertical line represents the activation energy with the catalyst. Now, look at the energy level diagram. Whatever the temperature is, if you have a higher temperature, then it will have an activation energy like this. If you have a lower temperature, the energy profile will remain same. That means the molecules, the number of molecules having low energy will have will be same. The number of molecules having high energy will be same. The number of molecules having average energy will be same. The difference is activation energy. Now, to start the reaction, the minimum energy to start the reaction will be lower. Earlier, you can see as we go to the right side through x-axis, what happens? Energy increases, right? Earlier, we needed more energy. Now, as the line is shifted towards left side, that means we need less energy. We need less energy, right? We need less energy to start the reaction. So this is how catalyst works. In presence of catalyst, more molecules have energy greater than activation energy. Now you can see the see this area. See this area. I have labeled C. Look at this, EAC. So in this side, if you draw some dashed line here, My annotation is not working, otherwise I could show it properly. Sorry for the unwanted problem. I'm really sorry, I am unable to show you. I don't know, the annotation is not working, otherwise I could do it here and I could show you. Anyways, so you understood that the area in the right side of EAC catalyst is greater than EA, only EA, right? That means more number of molecules will be able to participate in the reaction. Okay, so no problem, right? Let's go for the other question. Okay, let's go to this question now. D. Okay, this is a nice question. Two reactions involving aqueous sodium hydroxide are given below. See, in both reactions, sodium hydroxide is involved. In the first one, CH3CHBr, CH3 NaOH, CH3CHOH, CH3 NaBr. So this is a nucleophilic substitution reaction, right? And what type of, look at the reactant in the first reaction. Look at the reactant. This is a nucleophilic, it will undergo nucleophilic substitution reaction. Can you tell me what type of nucleophilic substitution reaction will take place? Will it be SN1 or SN2? Pressure is not 450 atm. Pressure will be 200 atmospheric pressure. 200 atmospheric pressure at best, and temperature will be 450 to 500 degrees Celsius. Safia, powdered iron will be used as a catalyst. This is correct, but the pressure will be 200 degrees Celsius. Sorry, 200 atmospheric pressure, and temperature is fine, 450 to 500 atmospheric pressure. Let's go back to this question very quickly. So CH3CHBrCH3, this is a 2 degree, right? 2 degree halogenoalkane. So 2 degree halogenoalkane will undergo what type of substitution reaction? Abdul Aziz. It would undergo both SN1 and SN2. SN1 and SN2. Zubair. What type of reaction will it? What type of mechanism will it follow? It will follow SN1 or SN2 both. We know SN1 is specific for 3 degree alcohol, 3 degree halogenoalkane, and SN2 is specific for 1 degree halogenoalkane. But for 2 degree, it could be SN1 or SN2, whatever. But it is giving nucleophilic substitution reaction. Okay. On the other hand, second one is an acid-base or neutralization reaction. Now come to this question. In order for reaction 1 to occur, the reagents must be heated together for some time. Reaction 2, however, is almost instantaneous at room temperature. What is the reason behind this? This is a nice question. This is really a nice question. In reaction 1, in terms of activation energy, we can tell that in reaction 1, higher activation energy is required to break down covalent bonds. As we have covalent bonds here, to break down the covalent bond, we need high energy. On the other hand, in the second reaction, basically the reaction will occur between hydrogen ion and hydroxide ion. You know, when you write the ionic equation, it will be hydrogen ion and hydroxide ion, right? Second reaction. Second reaction, Hanadi, you're right. Boys are inactive right now. They are not interested to answer at all. I don't know why. Be active, boys. Everyone is fasting, so you should not be tired. You should not be tired. Okay. You can answer me. In reaction 1, more activation energy will be required than reaction 2. This is number 1. Number 2, what is the reason? The reason is in reaction 1, we are actually breaking down the covalent bond. In reaction 2, what are we doing? In reaction 2, we are just carrying out the reaction between hydrogen ion and hydroxide ion. Others are spectator ions. Sodium ion, chloride ion, these will be spectator ions. Only hydrogen ion and hydroxide ion will participate. So opposite ions will attract each other, and the reaction will be faster. The reaction will be faster. You can Okay, so look at this. I can show you the reaction here so that you can understand what I'm trying to figure out. So I have written it here. Reaction 1, we have nucleophilic substitution reaction. I have drawn it here because it is a 2-degree halogenoalkane. You can see from the drawing. So it will undergo nucleophilic substitution reaction. Reaction 1 has greater activation energy because energy is needed to break covalent bonds. Reaction 2 has lower activation energy because basically the reaction is the ion equation. If you write the ion equation, it will be H plus and OH minus H2O. Opposite charges attract as the reaction involves ions. Okay. And the last question, state the reagent needed to confirm the presence of CHOH-CH3. Look at this. This is a secondary alcohol having CH3 group. And you know that it will also give the reaction of methyl ketone. You remember that iodoform test? So what are the reagents? We need alkaline, aqueous alkaline iodine, right? Aqueous alkaline iodine. And in presence of this one, it will give a yellow precipitate, right? It will give a yellow precipitate. Alkaline aqueous iodine, and it will give a yellow precipitate. Okay. So you understood this one. We have around 3 minutes left for today's discussion. I think we can discuss the next couple of questions, question number 3 and question number 4 onward, 3, 4, and the next class. Till now, if you have any question, you can ask me. If you raise your hand, I will definitely answer you. Adenine alka, yes, Shafia. Shafia, you are unmuted. You can tell me what your question is. Hello. Yes, Shafia, you can tell. You are unmuted right now.
Assalamu alaikum.
Walaikum
Yes,
salam
teacher.
warahmatullah.
For the second degree compound, SN2 is more preferred, right, teacher?
SN2, you can prefer SN2, no problem. SN1, but it can give both SN1 and SN2. That's what I was telling.
Okay,
SN1
yes.
is specific for 3-degree halogenoalkane, and SN2 is specific for 1-degree halogenoalkane. But SN2, 2-degree halogenoalkane can give both SN1 and SN2. Normally, we prefer SN2, right?
Okay, yes, teacher. Thanks, teacher.
Okay. Any other question? Anybody? You can raise your hand. You can tell me. We have around 1 minute left. So it won't be wise for me to start the next question. I cannot cope up with the time. Hopefully in the next class, we will discuss the remaining questions. Before that, I have a suggestion for all of you. You please revise organic chemistry. Before your next class, you revise organic chemistry. I hope you understood what I explained today, right? Especially, please follow my instruction. For the next class, you have to revise organic chemistry. Thank you, those who are giving me feedback. It's a pleasure for me to get feedback from you. Thank you for your active participation. Boys, I suggest you to participate more actively. If you have any question, still you can ask me. Yes, Tausif, do you want to say something? Okay, everyone, take care. Allah Hafiz, and revise organic chemistry.